This video is on titrations, titration curves, and calculations. So a titration is set up where we have a ring stand, we have an Erlenmeyer flask, and this is a burette. What happens is a titrant is put into the burette, and we titrate with the titrant into an analyte, and we are able to determine the concentration of our analyte. So a solution of unknown concentration goes in our Erlenmeyer flask. A solution of known concentration goes into the burette. And depending upon how much of our known concentration goes into our unknown concentration, we are able to calculate our concentration of our unknown. Lots of new words. So, inside the flask is our analyte and our indicator. The indicator, remember, changes colors based on pH. Our analyte is our unknown concentration. Our burette contains the titrant. Our titrant we release down into our analyte, and we record the volume of titrant used, the volume of analyte started with, and that with some math can tell us our concentration of our analyte. So, a titration is a controlled addition of a titrant used to determine the concentration of an unknown. The titrant goes in the burette. The titrant is the solution of known concentration. It makes sense that we do a titration with a titrant. The solution of unknown concentration is an analyte. This goes into our Erlenmeyer flask. We add titrant to our analyte until we have a color change. And the point when an indicator changes colors is known as the endpoint. This tells you you are done with your titration. The indicator is a weak acid or base that changes colors when the pH changes. Now, endpoint and equivalence point are two different things. The equivalence point is when there are equal concentrations of hydrogen ions and hydroxide ions. That is not necessarily the same endpoint that we are looking for, so it's good to know the difference between equivalence point and endpoint. When we get this data, we can make a graph. So while doing the titration, we want to record the amount of titrant added, and we can record the pH. Usually this is done using a pH meter, which would be inserted into the Erlenmeyer flask. A titration curve usually has an S shape, and this is for monoprotic acids, so acids with one acidic hydrogen. We start off by titrating our acid, so it's acidic solution. And it's acidic until we reach our 7. At a pH of 7, we are at our equivalence point, where a number of hydroxide ions concentration equals our hydroxide ion concentration. So they cancel each other out, and that gives us our pH of 7. They're equal. We can continue on, and after this point, we now have a basic solution. We read these by looking at our pH and the milliliters of titrant added. We can note that our equivalence point is at the point of inflection in our line. So again, the equivalence point is where there are equal concentrations of hydrogen ions and hydroxide ions. For a monoprotic acid, this is at a pH of 7. So we can graph information from our titrations. And like I said before, we can also record our volume of our titrant. We know our concentration of our titrant. And we can record the volume of our analyte. What we don't know is we don't know the concentration of our analyte. So to do this, we can do some math, some calculations to figure that out. To do this, we have a formula similar to our dilutions formula. We have concentration and volume, and concentration and volume. We separate these out with A's for acid and B's for bases. We'll notice that something new here is N. N has to do with the number of hydrogen ions in the acid formula and the number of hydroxide ions in the base formula. This is similar to their molar ratios. We'll do an example to show you how to do this. I want to know the concentration of phosphoric acid if 10 milliliters of acid is neutralized. That's our important word that tells us we're doing a titration by 20 milliliters of a 0.2 molar sodium hydroxide solution. So we set these up similar to our dilutions, except we're going to make a column for our acid and a column for our base. It's important that we write our formulas correctly. Phosphoric acid came from phosphate, so that's PO4. It has a charge of -3, so it means I have 3 hydrogens on the front. Sodium hydroxide, sodium has a charge of +1. Hydroxide has a charge of -1, so they cancel out. I want to know concentrations, volumes, and the number of hydrogens or hydroxides. My problem asks, what is the concentration of phosphoric acid? So that's what I'm looking for. If 10 milliliters of acid, so my volume of acid, is neutralized by 20 milliliters of 0.2 molar sodium hydroxide. So that's 20 milliliters of 0.2 molar sodium hydroxide. My number of hydrogens and hydroxides, so my N value, comes from my formula. So I have 3 hydrogens here, so N is 3. I have 1 hydroxide here, so that N value is 1. So I set up my formula, NaMaVa is equal to NbMbVb. So acids, which is my H3PO4, base, sodium hydroxide. I am looking for the concentration of my acid. So I need to divide both sides by NaVa. So I get the concentration of my acid is equal to NbMbVb divided by NaVa. So I'm going to plug in my values. So moles of my base, hydroxides is 1. Concentration of my base is 0.2. Volume of my base is 20 milliliters. And we can leave these in milliliters because they're both the same. Divided by my number of hydrogens, which is 3, times the volume of my acid, which is 10. When we plug that in our calculator, we get 0.13. I'm looking for concentration, so that's molar. So that tells me that the concentration of my phosphoric acid is 13 molar, so I write H3PO4, 0.013 molar phosphoric acid.